Welcome to episode 73 of 100 Days of Data. I'm Jonas, an AI professor, here to explore the foundations of data in AI with you.
And I, Amy, an AI consultant, excited to bring these concepts to life with stories and practical insights. Glad you're joining us.
The man who quantified information. That's the short way to describe Claude Shannon, a true pioneer in how we understand data and communication.
It's amazing to think how his work shapes everything from our phones to the internet. But who was Claude Shannon really? And why should business leaders today care about this math whiz from the 1940s?
Well, let's start with the basics. Claude Shannon was an American mathematician and electrical engineer. Back in the late 1940s, he developed something called information theory. At its simplest, information theory is about measuring information, not just data, but the actual content, the meaning you get when it's communicated.
So it's not just data bits flying around in the airwaves, but the value of the message itself, like when a customer sends a support email or when an automated system detects a fraud pattern. The information part is what drives decisions.
Exactly. Before Shannon's work, communication systems like telephones and radios were more about engineering hardware, wires, signals, frequencies. Shannon introduced a whole new lens. How do you encode, transmit, and decode messages in a way that minimizes errors and maximizes the clarity of what's sent?
And that translated into real business breakthroughs. Think about telecommunications companies. Thanks to Shannon's formulas, engineers learned the best ways to compress data and detect errors, which means clearer calls and faster internet. It made communication more reliable and efficient, which businesses rely on heavily.
You could say Shannon invented the mathematical language of communication. His famous 1948 paper, A Mathematical Theory of Communication, laid out concepts like entropy, which is about unpredictability or uncertainty in information. In other words, how surprising or random a message is.
Which is huge when you think about data compression. If you can understand what's predictable in your data, you can shrink the size, cut storage costs, and speed transmission. Every company, from streaming services to banks, benefits from this.
Yes, entropy measures the average amount of information produced by a stochastic source of data. So if you have a fixed message, there's no surprise, zero entropy. But if a message is totally random, entropy is high. Shannon found a way to quantify this, and from there, he showed the limits of how much you can compress or reliably transmit data.
I remember working with a retail client who wanted to optimize their customer feedback system. Applying ideas rooted in information theory helped them filter out redundant or low-value survey responses, focusing only on the most informative bits to improve products faster.
That's a great example. Shannon's vision wasn't just theoretical, it's the foundation of practical applications. Another important concept is the channel capacity, the maximum rate at which information can be sent over a communication channel without error.
Which translates to the networks businesses use every day, from Wi-Fi signals in smart factories to data sent between financial institutions. Knowing your channel capacity helps engineers design systems that perform efficiently but don't waste resources.
Right. Shannon's channel coding theorem tells us that it's possible to transmit data nearly error-free up to a certain maximum rate, determined by the channel capacity. This means with the right encoding and error correction, you can approach nearly perfect communication.
And fast forward to today, GPS, streaming video, 5G networks, email encryption, and even cloud computing rely on these principles. Every time you watch a video without buffering or your voice assistant understands you, Shannon's math is at work behind the scenes.
Another fascinating aspect is that Shannon's work laid the groundwork for later developments in AI and machine learning. Measuring information content is key to many algorithms, especially when training models to identify patterns or compress data efficiently.
That's true. In my consulting work, when helping companies build AI models, we often deal with optimizing data inputs and reducing noise, all tasks fundamentally connected to information theory. For instance, feature selection in predictive models can be seen as reducing entropy to focus on the most informative variables.
Exactly, Amy. Shannon himself didn't directly work on AI or machine learning, but his ideas about information quantification became a cornerstone for those fields. Think about decision trees or neural networks. They rely on principles of uncertainty and information gain, concepts that stem from his theory.
It's impressive how foundational his contributions are, yet how few outside of specialized circles really know his name. For businesses, understanding Shannon's theory helps demystify how data is transformed into meaningful insights and reliable communication.
I'd add that Shannon's approach was surprisingly creative and playful, too. Besides his professional work, he loved juggling, creating gadgets, and even building a machine to solve the Rubik's Cube. This combination of rigor and curiosity is a great lesson for anyone working with data.
Absolutely. In fact, his playful mindset reminds me that innovation often comes when you approach complex problems with both deep knowledge and a sense of exploration. In business, that's the sweet spot for AI adoption too, blending solid theory with experimentation.
Before we wrap up, Amy, do you think understanding information theory impacts how leaders make decisions about AI investments?
I do. When leaders see AI as a black box, it becomes a gamble. But when they understand that AI is about extracting meaningful information from data, building on concepts like Shannon's, they gain confidence to invest wisely, set realistic expectations, and guide teams effectively.
Well said. The clarity Shannon brought to the concept of information is as critical today as it was 75 years ago. His work continues to illuminate the path from raw data to actionable knowledge.
So the key takeaway here, Claude Shannon gave us the tools to measure and manage information, creating the foundation for nearly all digital communication and many AI technologies we rely on.
And by understanding his ideas, business professionals can better appreciate why data quality, encoding, and transmission matter, not just in theory, but in every practical system.
Next episode, we'll dive into John McCarthy, the father of AI programming languages and the guy who coined the term artificial intelligence. You won't want to miss it.
If you're enjoying this, please like or rate us 5 stars in your podcast app. We'd love to hear your thoughts or questions about Claude Shannon or information theory. Feel free to leave a comment. Your feedback might even be featured in future episodes. Until tomorrow, stay curious, stay data-driven.